Parklardan en önemli, bizim için önemli olan konu güvenilir olmak ve işini doğru bir şekilde yapmak. Bizim temel felsefemiz bu.
Burada planlama aşamasından uygulama aşamasına kadar işverenlerimize hizmet vermekteyiz. Su yapı, İngilizce'de water structure anlamına gelmekte ve böylesine büyük projelere imza atmaktayız.
Bu projeyi çok önemli yapan etken Çetin Barajı beton dolgu açısından ve RCC tip gövde açısından Avrupa'nın en büyük barajıdır. Bu açıdan çok önemli bir projeyi en kısa zamanda tamamladık. Çetin Barajı bulunduğumuz bölge Türkiye'nin Güneydoğu Anadolu bölgesi. Çok verimli derelere, akarsulara sahip. Burada biz yenilenebilir enerji projesi yaptık ve ülke ekonomisine bu projeyi çok kısa zamanda kazandırıp faydalı hale getirdik.
Allplan BİM projelerimizi geliştirmede yardımcı oldu. Özellikle baraj yardımcı yapılarımızın tasarımında, çelik barlarla donatılmasında ve donatı açılımlarında çok yardımcı oldu. Tabii ki bunun haricinde revizyon süremizi oldukça kısalttı. Dinamik nesneler sayesinde bunu başarabildik.
Bizim Allplan'daki ana ihtiyaçlarımız aslında modelden kesitlere geçtiğinizde donatı modellerini oluşturduğunuz makroların kolaylığı. Bu donatıları 3 boyutlu ve değişken yapılara konumlandırmanız için çok rahat ve akıcı bir şekilde makrolara ihtiyacınız oluyor. Bunu Allplan çok basit bir şekilde sağlıyor size. Diğer programların haricinde ayrı olarak tutuyorum Allplan'ı burada. Bu konforu bize sağlıyor.
Çetin projesinde Allplan bize karmaşık yapıların birbiriyle uyumunu çözmemize yardımcı oldu. Ve yapıların statik hesaplarını yaparken 3 boyutlu tasarlamış olduğumuzdan dolayı yapıları başka bir programa 3 boyutlu aktardığımız için hatasız analizler yapabiliyoruz. Allplan'da 2 boyuttan 3 boyuta geçmek bizim için çok büyük bir avantajdı. Çünkü hesaplamaları doğru ve gerçekçi modellememizi sağlıyor.
Su yapıyla birçok güzel projelere imza attık. Diğer bütün yatırım projelerimizde de su yapıyla çalıştık. Su yapı bizim bir alt şirketimiz değil, artık Limak bünyesinde çalıştığımız iş arkadaşlarımız olarak görüyoruz.
Bu projenin 6 ay önce bitirilmesi tabii ki çok ciddi bir proje çalışması gerektirdi. Bu proje çalışması sırasında Allplan bize yardımcı oldu. Özellikle revizyon yapmak istediğimiz zamanlarda hızlı bir şekilde dinamik nesneleriyle bunu başarabildik. Allplan'e teşekkür ediyoruz. Allplan'in geleceğimiz olduğuna inanıyorum.
Das Projekt Zugersee Ost, das ist eigentlich eine 15 Kilometer lange Bahnlinie, wo wir den Auftrag haben, komplett neu zu machen.
Die besteht aus rund 100 Objekten, Einspurtunnel, 7. Da hat man x Brücken und Unterführungen, die wir erneuern mussten. Wir hatten Stützmauern, relativ grosse Hanganschnitte, die wir sichern mussten.
Unsere Tätigkeitsbereiche sind vor allem grosse Infrastrukturprojekte, Autobahn-, Eisenbahnprojekte. Von der Studie bis zur Inbetriebnahme von diesen Projekten eigentlich, dass man nachher auch einen effizienten Bauablauf hat und dass der Bauherr eigentlich nachher auch ein wirtschaftliches Objekt überkommt. Und das ist natürlich auch wichtig für die Kostensicherheit.
Also es ist grundsätzlich mal sehr steil. Sehr steil und sehr eng.
Grosse Hangneigungen von bis zu 37 Grad.
Am Hang oben dran hat man Häuser, Strassen. Unterhalb hat man Häuser, eine Strasse und dann kommt eigentlich gerade der See. Von 1 Meter aufeinander trifft man von sehr weichem Material plötzlich sehr hartes Material an.
Und das hat natürlich auch dazu geführt, dass wir darauf angewiesen sind, dass wir ein gutes Terrainmodell drin haben.
Also ich finde das ganze Koordinieren zwischeneinander finde ich eigentlich recht spannend. Das fehlerfreie Projektieren finde ich sehr cool, wie die Zahnräder funktionieren und auch in einer effizienten Zeit.
planen und bauen. Das ist für uns eigentlich immer wichtig, dass man auch schon in einer früheren Phase der Planung auch daran denkt, wie wir das realisieren. Wir haben uns dann entschieden, das Ganze in Allplan zu integrieren. Und dass wir alle Daten in einem Programm hatten, haben wir eine massiv höhere Effizienz erreicht, nachher in der Ausführungsplanung.
Alle Daten, also auch die ganze Trassebau, Entwässerungen, inklusive Stützmauern, Brücken. Für uns am Schluss des Projekts ist es ganz klar die richtige Entscheidung, es so zu machen.
Wir haben eine Lösung, die uns eigentlich für die Planung, für die Ausführung, für Hoch- und Tiefbau und Strassenbau und Werkleitungsbau, und das ist eigentlich das, was so ein bisschen der Match ist zu unserer Philosophie und zum Programm.
Bei unserem Fall war es eigentlich für mich extrem cool zum Mitarbeiten. Plötzlich steht es draussen und die Leute sehen, dass sie anhand von diesen 3D-Modellen das Tunnelportal abgebaut haben, ist eigentlich schon noch wirklich verrückt, dass das irgendwie so möglich ist.
Es funktioniert so weit gut.
Und es macht auch stolz, wenn man nachher in so eine Strecke fährt und weiss, hey, da bin ich maßgeblich beteiligt gewesen, dass das Projekt zustande gekommen ist.
Ich finde es eine richtig coole Situation. Das ist ja das, was mich auch begeistert an diesem Job.
Ja, wir planen nur noch mit Allplan. Ja. Das ist eigentlich unsere Strategie.
Ich bin hier am Umsetzen eines Projektes, das man schon als Jahrhundertprojekt bezeichnen kann.
Genau, hier an der Bergstation Kölner Hütte kommt die neue Aufstiegsanlage her. Die alte war überholt und jetzt mit der neuen wollte man auch das Thema hier aufnehmen mit dem versteckten Rosengarten in einer Höhle, wo die Kabinenbahn jetzt ankommt, auch in einer Höhle und im Berg verschwindet sozusagen.
Speziell bei dem Projekt war dann noch die Herausforderung, dass man im hochalpinen Gelände ist, dass dann die Voraussetzungen vom Boden nicht so gegeben waren wie ursprünglich angenommen.
Weil wir in der Zwischenzeit einmal eine Hangrutschung hatten. Das Gelände musste neu vermessen werden. Das heißt, wir mussten laufend wieder die Vermessungen einholen und wieder anpassen in unser Modell und darauf eben auch reagieren.
Dies war ein ambitioniertes Projekt und dementsprechend haben wir gesagt, wir brauchen auch einen stabilen Partner, der auch die Kapazitäten hat, diese extremen Sachen zu rechnen und bereitzustellen. Grundsätzlich ist Holzner Bertagnoli eines der renommiertesten Planungsbüros in Sachen Statik, das wir hier irgendwo zwischen München und Mailand vorfinden können.
Unsere Schwerpunkte sind die Tragwerksplanung und die Geotechnik. Also mittlerweile machen wir seit 17, 18 Jahren, wo wir eben für die Seilbahnen die Tragwerksplanung machen.
Seilbahnen unterscheiden sich zum gewöhnlichen Hochbau eigentlich dadurch, dass man zusätzlich zu den Vertikallasten auch die horizontalen Seilbahnlasten hat.
Eine gute Planung ist immer wichtig bei allen Projekten, aber vor allem bei solchen Projekten, weil bei der Seilbahn hat man nur ganz ein kurzes Zeitfenster, wo man oben auf dem Berg arbeiten kann.
Und in den letzten Jahren, was noch dazu kommt, ist, dass die Seilbahnstationen nicht mehr einfache Zweckbauten sind, wie sie noch vor 15, 20 Jahren vielleicht waren, sondern kriegen auch immer mehr eine architektonische Wichtigkeit und Bedeutsamkeit und das alles noch spannender und noch schwieriger machen. Design to Build, also zu planen fürs Bauen. Das ist etwas, was entscheidend ist und andersrum würde es gar nicht möglich sein.
Ja, also Allplan ist für uns sicher die optimale Softwarelösung, speziell für solche Projekte wie diese Seilbahnstationen, die geometrisch sehr komplex sind, die herausfordernd sind.
Alle 3D-Zeichnungen, alle Bewährungsdetails, alle Mengenberechnungen erhalten wir von Allplan. Mittlerweile auch die 3D-Modelle des Geländes und die Schnitte und so weiter. Und das ist einfach für uns ausschlaggebend.
Also da haben wir einen echten Wettbewerbsvorteil.
Welcome back. We are moving forward to Allplan Bridge part. As you already know, Allplan Bridge is a parametric solution that allows you to describe and define the complete BIM process in bridge projects. But today, we will show you our latest innovation. We will show you a revolution in modeling of precast girder bridges. After that, you will see further new implementations which will simplify your workflows more than ever before. We are starting with Gregor Streckel, Product Manager for Infrastructure, who will present you a dedicated solution for modeling of precast girder bridges. See you later. Gregor?
Thank you, Jelka. Also, I would like to welcome everyone to our event. Please allow me to ask you something. Have you ever generated a complete 3D model of a precast girder bridge? If yes, how straightforward was the modeling itself? How exact was the final model? And were you able to reuse your data in subsequent projects? For what I have experienced, all of this was always a struggle, and many bridges of this type were and still are designed in 2D. But as BIM becomes more and more mandatory, modeling these bridge types in 3D is unavoidable. With Allplan Bridge, we help you to make this step effortlessly. And with this presentation and concluding live demo, we will show you how simple it really is. But before digging deeper, I will make a short introduction for all of you who might have never seen or heard about Allplan Bridge. I will very quickly present what the Allplan Bridge solution is and cover the initial modeling approach. The Allplan Bridge solution consists of 3 applications linked between each other. It allows you to use one solution and only one bridge model for the complete BIM-supported bridge design process, from parametric modeling to drawing production, including structural analysis and reinforcement design. This not only shortens the design process, but also improves it, especially because there is no data loss and there is no redundant data input. The data can be shared with the outside world at any time, and the final deliverables can be handed over in any format. The solution consists, as we see, of Allplan Bridge. So here we can generate an exact 4-dimensional geometrical model, from which then the analytical model can be derived and used for structural analysis and reinforcement design. The same geometrical model can be used in Allplan engineering for detailing and drawing production, and also in Allplan BIM+, which is the ultimate collaboration and exchange platform. In Allplan Bridge, more or less, everything starts with an axis. The axis can be either defined manually, or it can be imported as we have already seen today. In the next step, the typical cross-sections are defined. Here, the user has no limits because an arbitrary geometry can be defined and each parameter can be set as a variable. And for this parameter, any variation can be set. In the final step, everything is merged into 3D by extruding the section along the axis. And according to the designed relations in the cross-section and defined variations, the product calculates the final 3D geometry. This approach is applicable for all the bridge elements, for substructure as well. And once the main structure is defined, we can add tendons. We can assign any material, and we can even implement the fourth dimension. This is time by introducing the construction sequence. However, this advanced modeling approach is especially tailored for bridges with the geometry that is directly governed by the axis. But there are many bridges of different types and shapes, and some of their geometries are only indirectly governed by the geometry of the axis. Like, for example, precast girder bridges. This is why we are introducing a specialized modeling workflow for these bridges to allow you to generate an exact geometry easily and quickly. For this, many new features were implemented, and in combination with the initial one, any geometry can be generated. In the new workflow, first, the axis needs to be generated or imported. Then, the geometry of any section can be designed and used for definition of the templates. Now, the substructure with or without foundations can and must be generated. And now, same as on the construction site, the girders are positioned relative to the substructure. For modeling of the deck, again, the original modeling approach can be used. Now, we have to generate the haunch or fillet. Its 3D geometry is highly arbitrary, especially because it connects two bridge parts modeled with two different approaches. In Allplan Bridge, we have found a very simple solution for modeling of the haunch, and these are 3D Boolean operations. With this, the main bridge elements are modeled, and the model can be finalized as usual. The first new element type that we have implemented is link girder. It's a straight element, same as in the real world. In one simple description, we could say that a link girder is a 3D element between two 3D points. And these two 3D reference points define the virtual, a local axis, which is used for the calculation of the geometry. And from here on, again, the initial modeling approach can be used. And also link girder is, as all other elements in Allplan Bridge, a parametric element. A further characteristic that is common for prefabricated girder bridges is the repetition of the girder shape and length. Here, there are no limits, and despite the fact that for girders normally standardized geometries are used repeatedly, each bridge is still unique. The new modeling approach is open and therefore supports this. And to support also the repetition of the girder geometry, we introduced template-based modeling. Also in this virtual space, there is a virtual axis. And we can define as many templates as necessary for link girders and for pier elements. And for pier elements, it is vertical. And for link girders, it is horizontal. And from here on, again, the initial modeling approach can be defined and used, and so any girder shape can be generated. And once the template is finalized, it can be used in the main 3D model as many times as necessary. Important is that both the template and the target element in the final model are parametric. With this, the modeling is accelerated and changes can be incorporated very easily. They have to be incorporated only in the template and are then automatically adjusted through the entire 3D model. How exactly this works, you will see later in the live demo, which will be done by my colleague Jan, but allow me to give you a quick summary. First, the template needs to be generated. In the second step, so once the template is generated, the template can be used, and the link girder is positioned on the substructure by selecting the first and also this, of course, the second point. Begin and end excess length is a further property of the link girder and can be set directly in the modeling process or later in the property grid. And the same way, we can generate all other girders. Or we can simply copy these girders as many times as necessary. In this way, all girders can be generated very quickly. And I think now you can see why with this modeling approach, we can not only generate an exact model, but we can also speed up the modeling process itself. And when talking about the exact geometry, the girder length is, of course, the key point within this modeling approach. Especially when the section of the girder varies along the girder length and when for modeling templates are being used. Why? Because we do not know the exact length of the girder when modeling the template. The technology we have implemented allows both. So either the length of the template is same as the girder length, or that the length of the template is not important and the girder length is specified when positioning it on the substructure. So in this case, the girder is adjusted or just stretched. Which approach to use strongly depends on the bridge geometry and, of course, which one is more convenient. In both cases, the distance between the reference point RP1, as we can see here, and RP2 is given. It is, of course, set by the geometry of the substructure. Now, as I mentioned, so we can use the template length and define directly the girder length. So with this, we just have to fix or position this girder length, this girder length on the structure. Or, as you will see now, or the girder length is not important and the girder is stretched. So the girder length, the final girder length is defined when modeling the girder within the real 3D model. But what happens if, of course, if the girder geometry varies along its length? To solve this as convenient as possible, we have introduced new types of stations. In the case where the position of the station does not influence the final girder geometry, you can use a simple stations as until now. This will stretch and adjust in the same way, in the same relation as the girder. In the case when the position of the cross-section change is fixed, you can now use the new types of stations. So let's call them maybe fixed stations. And with help of this, it is possible to fix these positions of the variation. Using this, we can still adjust or scale the girder length, and the fixed stations will remain on their positions. This can be also seen in this picture below. In this case, of course, the same template is used, but as the stations are fixed, the begin and the end of the variation, at the begin and the end of the girder remains unchanged. Despite that, the girder length is, of course, stretched. And once all the girders are modeled, the next bridge element that can and must be generated is the bridge deck. And as the deck geometry is governed by the axis, again, the standard modeling approach can be used. Next, and almost last step, is modeling of the haunch. The basic geometry is given by the shape of the haunch itself. We could also say by its cross-section. On the cross-sectional level, also the cross-slope of the slab and the girder arrangement determines the geometry of the haunch. In the longer direction, the geometrical inconsistency between the plate and the girders characterizes the haunch geometry. The deck follows the axis, and with this also the elevation. On the other side, the girders are straight. This results in a variable haunch thickness. As just illustrated, the final form of the haunch can be quite complex, but we can also read out that the haunch geometry is more or less governed by its surroundings. And also, this fact we can use to our advantage. In Allplan Bridge, you just need to define the geometry of the haunch on the cross-sectional level. This is in the cross-section definition. And the final three-dimensional form of the haunch is automatically calculated and generated using 3D booleans. This is possible because all governing parameters are already defined. With this, the modeling of the main bridge elements is done. And now all other elements can be, all other details can be defined, like bearings, side curbs, and so on. With this, I am concluding my presentation, and I would like to ask Jan to join me here on stage and to show you how modeling of precast girder bridges is done directly in Allplan Bridge. Thank you from my side and enjoy the live demo.
My name is Jan, and also I would like to welcome you to our deep dive event and thank you for joining. First of all, I would like to thank Gregor for his interesting introduction in our precast girder solution. And at this point, I would suggest we deep dive directly into the software and see how it's done. So let's go. Okay, you can see that we are already in the 3D modeling environment of Allplan Bridge, and you can see that I have already prepared something. On the screen, you will see I have already two axes. One in the red color will represent the road axis. The one in the yellow color will represent the terrain axis. You can already see I have prepared some of the cross sections. If we take a look, we have our main girder cross section, then we have a hammerhead cross section, then we have two types of piers already defined here in the cross sections, which I will show you later why. But now now we know what kind of cross sections we have, what kind of axes we have, and I would suggest we take a look at what we're going to do. Okay, so for this example, I have already prepared a few templates. You've heard of them in the presentation before, but let's take a look before we start into one template. So this is the Pier template. You can see this is happening in a separate modeling environment, and I can create here templates that I can reuse over and over in the project. This template is a hammerhead pier. And I don't want to go too much into detail now here, because my colleague Dieter will explain later how it's done more in detail. But I think the important part to know here is that this hammerhead pier is defined like this, that this hammerhead at the top will stay at a constant height, but only these circular piers will change how we define them. We will see how this works. So I would suggest we go into the 3D model and start modeling our bridge. You can see I have two axes, and I will start modeling at the terrain axis, where I will start positioning the piles. So I will first say piles, for example, piles 1, is the name here, and let's see I can already move this template around. First of all, I need to select on which axis I will connect it. So this will be connected to the terrain axis now. I click on it, and now I can insert the station. I will say, for example, at 60 meters here. Okay, the next step is, you can maybe see already on the right side, we have in the properties some kind of geometric positions here. This will be geometric position 1, geometric position 2. And now what I'm doing, I'm defining geometric position 1. And we can see it's set to relative distance. And what will this mean for our object? It's, for example, if I set it at minus 25 meters, for example, like this means that that the bottom of the piles will always stay at minus 25 meters. So I mean 25 meters below the terrain axis, even if the terrain axis moves, for example, in height. So let's position it like this. Okay. So the next point is for the top of the pile cap. This one should also be connected to the terrain axis. So I will click again on it, select the station 60. And for this one, I will set an offset of 0. So the top should be directly the terrain axis. Okay, so our first pile cap with the piles is now defined. What I can do now is I can easily, for example, copy it. So just copy, rename it to P1, so for piles 2, and select then the station, for example, at 90. But before I do this, I will change this to relative distance again for the geometric position point 2. So 90. There I will just select any value now, let's say minus 21.6. And at the top, again, 0. Okay, this was the first step. The piles and the pile caps are positioned. And in the next step, I will position the pier that we have seen before in the template. I will use the same approach now of drag and drop inside the model. So let's just do this, pier 1, select OK. And the bottom part will also be connected to the terrain axis. So I click on the terrain axis, go to station 60, select the bottom offset, which in this case should be 0. But in this case, I will have an element connected to two axes because the top part should be connected to the road axis. So for this, I will now click on the road axis here, and I will choose the same station in this case, so 60, but I will set a vertical offset of -2 meters, like this. Okay, so we need one more pier. I can just drag and drop it again, position it above the second pile cap, so this will be at station 90, set the bottom distance, the bottom vertical offset, which should also be 0, and then connect the top part to the road axis at station 90, like this, and with the same vertical offset of -2 meters. Okay, before I continue maybe here with modeling of the piers, I would like to show you what happens if I make a change to the template. So in this case, we see we have circular piers, but what if I want to change the cross-section, for example? I can easily go into the pier template, go into the cross-sections, and just assign, for example, another cross-section for the rectangular one. I can just use our excellent drag and fill function, recalculate, and we see that the shape has changed in less than a second. Okay, in the next step, I will position a few abutments. Just take a look at the template of the abutment. This abutment is defined like this, that if you see this top side, and this top structure of the abutment, this one, yeah, this will stand constant at any point. The only part of the model that will change in value or in height are the piles, and we will see how it works. So I will use the same functionality, drag and drop, abutment 1. I will just say here, for example, abutment 1, hit OK, and I will position this one at 30. Okay. Now the bottom position, the bottom of the piles, we will, let's say, at around -20, and then just again position the top at 30, and I will set a vertical offset of -0.5 meters. But what I'm seeing now is that this abutment is facing the wrong direction. This is also no problem. I can easily click on the abutment like this, and in the properties on the right side, I have this pier rotation. So this pier rotation can be then 180 degrees, recalculate, and the abutment is facing the right way. Okay, we need one more abutment also on the end of the bridge, so I will just use copy, abutment 2, okay, set the geometric position for relative distance, and position it at a station of 120, like this. Bottom position, let's say here also -20, and then the top position will be at -0.5, like this. Okay. Both abutments are set, also both pile caps and both piers are ready. The next step is, as you've seen also in the presentation, how we position the link girders. We will use the definition type between two reference points. But first of all, let's take a look at the link girder that we have prepared in the template and explain its geometry a bit. So we have here a nice template of our precast girder, and you might notice there are some slight geometry changes there. So at the beginning, it's a bit wider, then it gets thinner, and then at the end, again, wider. And we have defined it like this, with the new types of station that my colleague Dieter explain later. We have defined it like this, that the first 3.5 meters are a bit wider, then according to what distance we define, the middle part is thinner, and then also the last 3.5 meters are again a bit thicker. Okay, so let's position now these link girders. Drag and drop the first one. I will just rename them one, let's say 1 - 1, so that will now span 1, girder 1. We will see later why. For the numbering, it will a bit more clearly to see where they're positioned. So I select this geometric point, I mean the reference point 1, and then the second one, and the girder is positioned. But now I can use this multiple copy functionality and continue copying these elements. So now we'll do this for the first span, like this, and just select this reference point in the 3D model, oops, like this. I just need to select the right one, yes, here, also here, and the last one in span 1. Okay, span 1 is now complete, we just have 2 more spans to go. So we can see how fast and easily this works. So here we change the span to 2 and start again with the numbering 1. So we will know exactly which span it is. Like this. Okay. Here, second one, third one. Also need to select the correct reference point here, like this. And also the one here. And of course, the last one. Yes. Okay, don't get distracted, but all these values that we have here, because we can turn them off, all of these yellow reference lines, maybe you will just turn off, for example, the station values here, and we have a more clear representation. Okay, one last span to go. I will just use multiple copy the last girder. So select here span 3 and start again with the number 1. Select this and just keep clicking. And we are almost done with our last span. So just 2 more to go. And what you might have noticed here with these precast girders, that maybe the distance when it comes to the hammerhead position, they're a bit wide apart, but we can change this in just 1 step. So I don't need to go into the template again. I can just do this now in the 3D model. So for example, I can just select all of the girders here, and I have some kind of exceedance length. So the exceedance at the begin and the exceedance end. And this will go over the length that has been defined. So just let me demonstrate this by, for example, at the begin, I will go with minus 0.5, and at the end at 0.5. Recalculate, and we see that they are now closer together. Okay, now at this point, I would like to show how, for example, the link girders change if I change something in the model. For example, if I change the position of the pier. For this, I will move this pier that we have here, that we have defined. First, I would move it a bit to the left side. So I will start by first repositioning the pile cap, and let's say, for example, 50, like this, here, and let's go to pier 1, should be also at 50, recalculate, and we see that the link girders have shortened and the pier has been repositioned. Okay, there is one more feature that I would like to show before I continue, is that we have now also custom trees. And this will come in handy if you have multiple spans of link girders, and there you can easily organize your 3D model, your tree, your geometry tree. So if you go to the custom trees, I can then just create a new custom tree. For example, I can say new tree item that I can name span 1. For example, I will just create one for span 2 and a free item for span 3. I can then just easily drag and drop. Now you see why I have numbered them that way. And I can easily select the elements now from the first span, just click and drag them into span 1 into our custom tree, like this. This will then also help you with the defining of the construction schedule, because you will have a more clear organization of your model. Okay, there is a few more things to do. And the next, what is our model missing, is, for example, the deck. And I will go on to the deck. I have created a master deck, so this is also in a separate modeling environment. But I don't want to go too much into detail with these master decks, because I will have this explanation for you in a later presentation. But this master deck that is created here, we see also both axes here, can be then easily imported into the 3D model. And this can happen by just drag and dropping inside. So this is the deck. But do not be distracted now by this functionality where I need to select the first cut station, because we will also explain this in a later presentation. So here we just go with the starting value and the value of the cutting angle 0. We don't do any cuts here. And also the last one with also the angle 0. Okay, nice. We have the deck now in our 3D model, but I think there is something missing. And of course, to show you what is missing, I will hide this abutment by selecting it and adding it to hidden objects. We see that there is still, we have some empty space between the link girders and the deck. And for this, as you've seen in the presentation before, we are going to use our 3D Boolean operations, and this will be the haunch Boolean operation. And this will connect the link girder between this defined empty boundary here with the deck. And let me demonstrate this, how this works. I will click on the haunch. First of all, I'll select the deck and then select the according boundary. Select. After a few seconds of recalculation, we see that the geometry here between and the connection between the deck and the link girder has been created. Maybe let's create another one. So select the deck and select the boundary. But I would like to emphasize here that once I created these 3D booleans, these 3D operations, these 3D haunches, also this stays parametrical. And let me show you this. So I will show all objects again now. We have the abutment here. And what I'm going to do is I will first move this pier to the position it was before, just to demonstrate that also this haunch will get longer in the model. So if I go, for example, to pile cap 1, and I will move it back to 60, like this, here, and to pier 1, also define the station to 60 again. I can then recalculate the model, and we will see that also this haunch will adjust, as you can see right here in the model. So the whole gap between the link girder and the deck is still filled. Okay, last but not least is what if the alignment changes? So let's change the alignment. We have both axes here connected parametrically. You will also see this in a later presentation when we talk about the accompanying axis. And for this axis, I would just change the axis plan. I will change the radius from -250 to, let's say, to 550, like this. Go to the 3D model, do a recalculation, and our whole model, all of the link girders, everything will adjust, all the haunches, the decks, so all parts of the model adjust parametrically in just a few seconds. With this, I would like to conclude my presentation. I hope you've learned something interesting, and would like to give my word to my colleague, Philip. Thank you.
Hello everyone, my name is Philip and I'm here today to speak to you about the news implemented in Design and Check module in Allplan Bridge version 2022. Let's say about the highlight of this version is the implementation of American Highway Standard and all related features. We have also extended or enhanced Eurocode checks and design, and we have also updated few things in general features. So let's start probably with the first, and that is AASHTO standard implementation. We have implemented AASHTO in version LRFD 9, and this allows you to design and check all concrete bridges to the strength limit state, service limit state, and also fatigue limit state. To be sure that this bridge is buildable and it complies with the detailing rules, we have also applied the checks. This gives you really good information if your bridge design is safe and sound according to the standard. Let's dig deep a little bit into separate checks. The first one being the Flexure Check, which has already been released in previous version as the first out there. And basically you can check if the flexural capacity is enough to bear the loads. It's done based on interaction 3D surface, and it gives you also the response directly to the acting internal loads or internal forces. Also, the equation for the ratio of acting and resistant moments is applied, and this can be done not only for the girders, but also for the compression members such as piers. The second check is shear check, so mostly near or above the supports of the bridge. As you can see on the picture, there is a fully automatic solution that detects the shear effective parts for horizontal and vertical shear. This is done by the linear distribution of shear stresses in the section. This can be done for any arbitrary section. A very analogical approach can be applied also to the torsion. It combines the effects of both torsional unit stresses and finds equivalent thin wall section effective for torsion. All reinforcement or tendons lying within this area are considered. Flexure, shear, and torsion are not evaluated only independently, but they are also combined and they are assessed as a complex loading of the beam or of the section. And by this, we need to reach equilibrium between longitudinal reinforcement, transversal reinforcement, and concrete compression diagonal strut. Not just the strength limit state is crucial for bridges, but in case of prestressed bridges, service limit state is usually the governing one. So to do that, the user can use stress limitation check to see if his design is correct. He can do it during the whole lifespan of the bridge at any given location in the model. As the AASHTO standard defines it, the compressive stresses need to be restricted somehow in the slender parts of the section. Therefore, we implemented a slenderness reduction factor phi W in the definition of the stress points. User can easily define it. Also, he can vary it by the table or a formula. And in addition to the stress limitation, in service limit state, user need to tackle the crack width or crack control for the bridge. In Allplan Bridge version 2022, user has 3 options to do his design. The first one being excluding tension at all. This is sometimes done by putting more tendons resulting into higher pre-stressing forces in the section. But this might be typical also above or near supports of the bridge. The second more typical one, when we are more economic with our design, is to allow some tension to form. But we need to be sure that this tensile stress is still within the limits of the code. If this is not enough for us, user can also reach higher tensile stresses, but he needs to check the cracks itself. There are actually 2 options how to do that based on the equations provided by AASHTO standard. The first one is rebar spacing calculation, and the second option, which user can really influence, is the direct crack width calculation. We have also enabled the user or project-specific limits based on the exposure factor, which we will talk about a little bit in a minute. As you can see, all the results in Allplan Bridge, and specifically in design and checks snippets, are currently not available only in SI units or metrics, but they are also available in imperial units. The last but not least, from the AASHTO standard, is fatigue check. We need to tackle fatigue checks if the stress levels from the live load are not lower than the compression reserve coming from permanent loads. The fatigue is evaluated for all components of the section, meaning concrete, rebars, and also tendons. The constant amplitude, fatigue threshold, and corresponding combinations are evaluated automatically, and they are used and compared against the limits to reduce the utilization of the section. And we have also covered the minimum reinforcement check that is actually provided to avoid the brittle failure behavior of the section. We are telling that by providing an adequate amount of non-pre-stressed tensile reinforcement and pre-stressed reinforcement, that a sufficient flexure capacity is developed. This flexure capacity needs to be at least the lesser of factored applied moment or cracking moment of the section. For both AASHTO and Eurocode standards, we have implemented also some basic detailing rules check. This check basically checks the clear distance between the rebars. It checks some minimum or maximum reinforcement areas, and also checks it not just for longitudinal ones, but for transversal ones. As we have been speaking about Eurocode, there is also extension for brittle failure check, which was missing in previous version, so we have added it to be complete. For prestressed sections, it's based on reduction of the prestressing area, and together with reinforced concrete, we find a state where cracking appears in one of the fibers of the section. To make AASHTO standard compliant checks and design possible, we needed to add a few things to already existing property sets, or so-called reinforcement sets. The first one, mostly for service limit states, is the extension of exposure zones according to AASHTO for no, moderate, or severe exposure conditions. Of course, per project-specific reasons, user can define also a special type of exposure zone and define exposure factor gamma E up to his needs. Also, when we mentioned the imperial units, currently user needed to input a diameter to all reinforcement sets available in Allplan Bridge. In this version, user can work with bar sizes in imperial and metric systems. For more advanced user that wants to study the calculations detailedly, or in case of Eurocode, maybe to simulate different national annexes, we have implemented also some setting dialog for design and checks, so-called DC setup. This allows you to change any value given by the code, save it, and run or perform the checks accordingly to the new values. Also, not all countries in the world share the same terminology, so previously we have released the terminology of ULS check and SLS check that is mostly compliant to the Eurocode. As we wanted to implement AASHTO and possibly in the future many other codes, we wanted to come with some independent name that would allow easy input for a user for any standard. Therefore, in the new versions, everything will be done together in one task, that is code check. By this code check, if you try to input the new or modify the old task, you will end up with a new dialogues for code design and code check that are specifically tuned to the selected standard, so you will have a specific terminology and filters, for instance, for combinations applied. So just to conclude, we have gone through the news, the one being the AASHTO, obviously. Then we have enhanced few things in Eurocode and has also tackled the general workflow. I really encourage you to try it and give us your feedback. And now it's my turn to give my word to my colleague, Dieter Wagner.
Thank you, Philip, for this interesting and short intermezzo to the code design of Allplan Bridge to show us the possibilities also in that area. And now let's go back to the modeling. My name is Dieter Wagner. I'm Senior Consultant at the Competence Center Allplan Infrastructure in Graz. And in the next 30 minutes, I would like to show you our new possibilities regarding the pier definition and connected to that, the new possibilities using our new station types. To do so, I will first give you an overview of the possibilities of the theoretical background, and in the second part of my presentation, I will show you a practical example that will illustrate these issues. So let's first have a look at the possibilities. As you already know from the previous versions, the only possibility for defining a pier axis up to now was using a reference point in the cross-section of a reference girder. So that means up to now it was always required to have a structural member of the type girder where we could link the pier to. Now, with the new approach, the first possibility is to directly link a pier to an existing axis without having to create a girder in advance. The second possibility would be to link a pier also between two axes, for example, a bridge axis and a terrain axis, as you can also see in this picture. Finally, the third possibility would be to link the axis between a bottom axis and a reference point in the main girder. I will show you in a second an example for each of these three cases. Just to mention, we also have the possibility now to define the stations in the pier by an absolute height. That means previously you needed to relate to the local stations of the girder, and now you can also use the heights directly from your project for defining the pier table and the bottom of the pier. So, but let's now have a look at each of these new possibilities. The first one was linking a pier directly to an axis. So first I select the axis, I select the station point where I want to link the axis to, and then I can define the bottom and the top of the pier either by a relative distance to these selected station points or by an absolute height. So in this case, the absolute height was chosen for the pier bottom, and the top is linked also by an absolute height, or by a relative distance, sorry. And in the second example, we will link the pier between two axes. So first I pick the bottom axis as a terrain axis, and also defining the pier bottom by a relative distance, and then related to the bridge axis, I define the top of the pier. We are using here automatically applying of stations just at the beginning and end of the pier, as we have no variations in between. In the third example, we will link the pier between a bottom axis and a certain reference point of the main girder. And we will apply now changes to each of the three examples to see how the pier behaves. In the first one, we have linked the pier to one axis, the bridge axis. I will move it now a bit to the left, and you will see that the bottom, which is defined as an absolute height, will stay at its level, but the top of the pier, which has a constant distance to the bridge axis, will move down a bit due to the profile, which means the pier gets a bit shorter. And you will see in a minute how this can work. In the second example, we have linked the pier between two axes. Again, here we will move the pier a bit to the left by just changing the station values at the top and bottom. And you will see again at the bottom, the pier will now follow the axis of the terrain. and the top of the pier will behave in the same manner. So again, this pier gets shorter due to these new definitions, which I will show in a minute. Finally, in the third example, where we've linked the pier between the terrain axis and the girder, a reference point of the girder, the bottom will behave the same as we've seen before. It will move along the axis, and the top of the pier will follow the position of the reference point, thus following the geometry of the main girder. How is this all possible? So, as you know, up to now, when you were defining a pier, you always needed to relate to the local stations. So, when you defined the pier axis, the reference point was the origin of the local station. So, in our example here, this would be this position. And you always had to define all the stations related to that point. Now, with the new definition possibilities, we will define a so-called reference length. In this, I will explain in detail how this works, but just that you know for now, this distance here, named as relative, would be our reference length. And at the end, this is our end position of the reference length. And now we can relate also to that position, to that end position, and define stations related to that end positions. And we can define relative stations in the area of the reference length. I will explain now how this works. Just one comment before. Also here, you're free to use our new definitions of the global heights. And these new station types, they are not only limited to piers, but they are available for all structural members, the girders that you already know, but also for the newly implemented link girders. And it comes especially effective if we are using these station types with templates, which I will show in my practical example. But now, let's have a look how this pier, which we just have seen, behaves. Again, when we move it, if it's linked to two axes. So you can already assume that the height of the pier will change again. But as you see, I'll just make a brief stop here. You can see that the foundation and the hammerhead, having fixed stations, will geometrically remain the same, while the pier leg will adjust according to the height. Of course, the same behavior we have when we are changing the profile of the terrain axis. So we'll just move this point a bit up so that it changes the bottom axis. And after the recalculation, the height of the pier will again adjust without changing the hammerhead and the foundation. And now let's have a closer look how this is possible. As already mentioned before, there is an additional definition required now in order to use these new station types. And this is the reference length, which is defined by two geometric positions. We call it geometric position 1 for the start point and geometric position 2 for the end point. And in between these 2 points, the reference length is defined. And because this reference length must not be negative, we always must go in positive direction. So, but let's first go a step back just to see how it has been done up to now, where we just had the possibility to link a pier to a reference point. So using the new terminology, we could say that also this was already the geometric position 1, which defines the origin of the pier axis and my local station 0. And related to that, I could then define the stations of my pier. And with a new approach, there is one more definition, which is the definition of the geometric position 2. So in this case, as I said, we need to go in positive direction in order to have a positive reference length. I will put the start point, the geometric position 1, at the bottom of the pier. Again, defining the local station 0 of my pier axis, the same as before. And now there's just one more additional input of the geometric position 2, which defines the end position for using the local end stations, and the reference length for using the relative stations. That's actually everything you need to do in addition for using the new station types. And from that point on, the further definition is the same as before, so you can define your stations. And it's important to understand that you're not limited to that geometric position in order to define your stations, but you can go there in any direction from top to bottom, from bottom to top, or also outside the geometric positions. So this is completely independent. To illustrate that, I have the same pier once more on the right-hand side. And this time I will just put the geometric position a bit downward. It wouldn't make sense maybe in that example, just to illustrate it. And I will put the GP2 at the reference point of the main girder. Thus, when we define our stations, I will just have a different reference point related to that station definition and the different reference lengths. But you can see I can define exactly the same pier once again. Now we want to put in together in a live demo a bridge as seen before in the example from my colleague Jan. And in this example, as you have seen, we have a variable pier lag. So this should adjust according to my geometric situations of the axis. And the hammerhead would be fixed stations. So how can I implement this in the program? First, of course, we said we want to have this part of the pier variable. So, of course, then I would choose the geometric position 1 at the bottom of the pier and the geometric position 2 at the top of the pier in order to result in a reference length like this, where I can then apply my relative stations. And when we're defining relative stations, they are always related to a reference length 1. So it's a unit length in order to apply these relative stations. That means at the origin, the value of the relative station will be 0, and at the top, the relative station will be 1. And in between, you have the fractional values accordingly. And the advantage of this, you see on the right-hand side, when now the length of the height of the pier is changing, the reference length will get bigger, and the relative station will be placed in the same relation as before and will then be multiplied by the real length of the pier, thus resulting in the real local stations. After that, I also want to define the hammerhead, and now, of course, it would not be appropriate to refer to the local position, the GP1, because when the height is changing, the stations related to that point would also change. Therefore, I also use a new station type, refer it local end to the geometric position 2, because if I relate the station to that position, you see they are always related to the point, and from that point, they will be fixed. So let's now move to the program in Allplan Bridge to see how this works. I have already prepared two axes, so one axis simulating the terrain and one axis simulating the bridge axis. I have just applied a simple cross-section, so this would be like the bottom of any cross-section you might have, just that we can see it more nicely, what we define in between. It's just a slim section. And now I want to prepare a template for the pier. So of course I could directly define the pier and copy it along my axis. The advantage of a template is, of course, I can reuse it multiple times, but all piers created from one template will be related to the template. That means if I change any geometry in the template, it will be taken over for all the piers that I've created from the template. So to create a template, I go to the 3D modeling, and I have here a new function for creating a template for a pier. And then I would just take over this name pier for the template. And you will see the program directly jumps into the interactive definition. But let's just have a look first at the navigation tree. You see that this pier template is also added in the navigation tree as a normal pier, but just to identify it, it has an additional letter, a symbol here, T for template. And it has the same submenu station cross-section variation as a normal pier, so you can work as usual. The first thing now, when we define the pier in the 3D model, would be to define the geometric position 1. However, when we are using a template, the program already takes over this step for us, because I don't need to define this because I'm here in a virtual space, right? So this is just a template. So the program already assumes the geometric position 1 at the fictitious level 0. So starting from that, I can directly start with the positioning of the geometric position 2, which in our case would be the top of my pier legs. So first I change to the correct cross-section pier. And what's also new here is that I can directly, while inputting the pier, do some settings in the property window. And I will show you then in the next step what is the difference between the stations. But now I already want to tell the program that I want to have a free subdivision. So you can see we have here new possibilities to automatically set the station just at the beginning and end of the pier, or make equidistant subdivisions. But in our case, I want to have it free. And then I define the position. And here, it doesn't matter which value I put in here, because you know it will be overwritten later on. It's like you're defining a cross-section template, and you know you want to use a variable height later on. It doesn't matter what you use for drawing. So I just will use the value, some reasonable value, maybe 10. And in this way, I have defined my geometric position 1 and 2. And you can see, I'm sorry, now you can see that I can, of course, go below and above these geometric positions to define my stations. And now you see the difference. If I, for example, want to define local stations, they will relate to the geometric position 1. So they will be positive upwards, negative downwards from the GP1. If I use local end stations, they will be related to the end position of the reference length. In our case, we want to use relative stations. So I just click relative stations, and I will now start at position 0 and go up, as I mentioned before, to the position 1. This is now our fictitious unit length. And I want to have maybe 10 subdivisions. So I will take 0.1 meter steps, apply this, and in this way I have created my relative stations. In the next step, I want to define my pier head, and here I want to use local end stations. So first I change the cross-section to the pier head and change to the local end station, and now I'm relating to that GP2 position. First I want to go from that point on 1.5 meter up and then 2 meters. So first I click 1.5. I will just have one subdivision here, and then I get another up to the station 2, also just one subdivision here, and in that way I could go on. In my case, the definition is finished. I click escape, and of course we will apply the variation in the next step, but you can see here now my template has been created. And if I go to my created pier and have a look at the station menu, you can double check how we have defined the stations. So from the position 0 to 1, I have the relative stations, and then I have local end. So of course you're free to change. For example, at that position, it's clear that this intersection position where we have the relative station 1, this equals the local station end 0. So if I change the type here, you will see that the program jumps here then to the input station 0. And of course, then you can also see the evaluated local stations according to the height. At the moment, we have used the height 10. So by multiplying these fractional values, you come to the real local positions. Okay, let's first apply quickly the variation. So in my pier head, I have some variable width defined, and for this, I will now define a table. I will just call it V. And now we need already to think to which part we want to apply. So of course we want to apply to the pier head, and here I have used local end station. So I need to refer in the table to these input values, 0, 1.5, and 2. So I just put them in, 0, 1.5 and 2. And then we have half of the width. It's from 3 to 5, and then it remains constant. And this table we want now to assign in the variation menu, as usual, to the station of the pier head. And now you will see when I drag and drop, so I do not want to assign it along the whole pier, but just here in the bottom. So I will just assign it first to one station. And you know, previously we just had the local stations for the piers, and also for the main girder, we had by default the global station, and you could manually change to the local station. But now, as we have even more station types, there will be some window where you must now select which station types you want to use. So in the table, we have used the local end station as well as in the pier definition. So therefore, I can now change selected option, and you will see that now this argument, this internal variable, is now $SE for local station end. And in order to apply this to here, I can use the new drag and fill functionality. Just click this blue box and drop it downwards. And in this way, after recalculation, I can also see my pier template. So you see that the pier template is defined in a separate window, so it's not part of the 3D model at the moment. This is now our last step. So I will go now and make from this template, create a pier from this template. And I have two possibilities to do so. Either I go to the 3D modeling function and create from the template a new pier. Of course, then I have to select from which template I want to create a pier. This would be the first possibility. Or I simply drag and drop the corresponding template to my drawing area, and I can directly proceed with the interactive input. So maybe I will change to the transparent view. And now, of course, the first step is now to define the geometric position 1 and 2 in order to place the pier in the 3D space. So our geometric position 1 is the bottom of the pier leg, and this I will link directly to the girder, to the terrain axis. So I first click the axis, then I select the station where I want to link it. In my case, it's, for example, 25. And then I want to define at which height it should be linked to. And again, here in the property window, I can directly select, for example, the absolute height, which will be here at level 90 or something. But in my case, I want to directly link it to the axis, and I will choose relative distance and offset 0. So it will be directly placed at that point. And the second step, I will define the geometric position 2, which will be this point. So I need to relate it to the top axis and go a bit downwards. So first, again, I select the axis, I select the station, and again, I will choose relative distance for defining the offset minus 2.5 in my case, so that I have some space for the bearings as well. And you see that now the pier is created with the corresponding height of the legs and the constant geometry of the pier table. Just to illustrate once more how nicely this works, I will make one more pier at the end of the axis. So again, now very quickly, I will just first select the axis, type in the station, select the relative distance 0, go up to the top axis, again select the same station, and the offset minus 2.5. And you see that now at this point the legs are much higher, but of course the pier table remains constant. So that's a very nice way to make this completely parametric. Just one, before I finish my presentation, some more remarks. You see that the piers created from a template, they will not have a variation menu because this is taken from the template itself. You can see informatively the stations, the calculated stations. For example, my first pier, its real reference length, you see it's 5.88, and based on that, the program now can calculate the real local stations. One more remark, you see that also when I go to the pier, to this pier in the property window, you can see that this is a pier that is created from a template, from our template Pier 1, and I can unlock this, right? So I can choose, this should not be anymore a template, and you see, now it becomes again the usual menus, which I can edit, and now it can be treated like a normal pier anymore to the template. On the other hand, I can use a normal pier that I have directly defined in my 3D window, which would be, for example, the Pier 1, because I just have unlocked it, so it's now a normal pier, and I can use this as a template. So even after defining it in the 3D model, I can make this pier as a template. If I do so and recalculate, it should disappear, because now it's just a template, which I can now use for further modeling. Okay, I hope you could get an impression of the possibilities of these new modeling functionalities. And I will give now to my colleague Mobile with the next interesting topic.
Hello and welcome. My name is Moal Gassasa, and I will be today presenting to you link girders and IFC. To start with, what are link girders? So link girders are a 3D element that are placed between two 3D points. So a 3D point can be placed in a reference point or in an axis, in a station axis. These reference points are first defined the cross-section, then later assigned to the girders and piers. Of course, you have seen this example previously in the previous presentations, where my colleagues were showing you how to place link girders, or specifically precast girders. So the main objective of link girders are to use them or to place them in precast girders. Of course, we can use them also further for different use cases. The reason which makes them really powerful is because they have some specific characters to them, such as the parametric element. Of course, all the objects or the elements in Allplan Bridge are parametric. This also makes sense when we see the link girders are also parametric. And of course, there is also the characteristic, which is the template. Link girders are based on template. So if you have different objects which are based on one specific type of objects, you don't have to change each and every object, but rather what you do is you just change the template. So this also makes link girders really powerful tools. Of course, there is also one limitation. Of course, there is only one limitation, which is link girders are not, or we cannot reference link girders to another link girder. So this is the only limitation. But regardless, they are really powerful tools, or which are the new feature in the new version. Today, I'm going to show you some use cases that we can use, that we can show you, or you can use out of link girders. The first one, as you can see, is just a plain cable or a plain element which has two control points. These two control points are then placed, one in the reference point and the other one in the station axis. Then we use this to place, for example, the cables between the main cable and the main girder. Of course, as you can see, we can create a cable pedestrian bridge. Another use case, which is in the similar group, is also this cable stayed bridge. As you can see, we have cables which are placed between two cross sections. So we use also in this case link girders. Another group of use case that I want to show you is also the template. So here, as you can see, we have, like I said, since it's a link girder, we have two control points. We use these two control points to place this object or this element. Of course, as you can see, we can place this and we will have an object or we will have a project which looks like this. So the key idea here is that since it's based on template, you don't have to change each and every element, but rather you just change the template or the main object, then you can change all the other elements as well. This I will also demonstrate later in the demo, which is also another use case which is also similar in this group is also this truss bridge. As you can see, this truss bridge, it doesn't make sense to change each and every element, but rather you have it in one template, the main object, then you can change, for example, the cross section or the section or even the type of the cross section just in this template. So instead of changing each and every element, instead of changing this and every element, what you can do is you just change the template and you will have easier workflow. Of course, this also applies for this use case. In this use case as well, what the main objective of this use case is to show you how you can change the cross section, the end cross sections. What I mean by that is, for example, as you can see here, we have the piers, which has cross section which is horizontally slanted. So in this case, it becomes easier to change the cross section at the end, so you can change it to vertical, horizontal, or normal. I will also demonstrate this use case more later, so we can understand it much more easier. But the idea or the main message here is that it's easier to change the end cross sections at the end, as you can see, or for example the pier at the beginning of the pier, how it becomes easier to change the end cross section. The fourth use case is also here. It's also based on the parametricness. Since I said that before, link girders are based on the parametric, which also makes sense because Allplan Bridge is based on the idea of parametric. So it becomes also easier to assume, or it becomes also easier to create parametric elements. This also applies for the link girders. So the link girders, as you can see, it has two control points, but the rest of the object is a parametric with a varying width as well as a varying height for the object. So as you can see, we can place these link girders using these 2 pointers across our bridge. This is parametric and we can change it. Of course, we will also change it in the demo, the object, so it shows you how parametric it is. I will demonstrate now the use cases that I have mentioned so you can understand much more easier. So here, as you can see, we have the bridge. This is the first example that we showed. So we have this bridge and this is based on the link girder. So this is our link girder and the element is used to place it between the main girder reference point, which is here, and the axis. So we can place it between these 2 pointers regardless of the shape of the axis or the main girder. The link girders will be placed between these 2 points. To show you the real power of link girders, for example, I will just make a minor change. I will change the profile of the axis. Here, as you can see, I have a main axis and I have 2 accompanying axes. These 2 accompanying axes are used then to create these main cables, these 2 main cables that I have. And from these 2 main cables, I was able to create or to place the link girders between these 2 main cables, between the main cable, this one, and the reference point, which is on the main girder. So the idea here is, even if we change the axis for the main cable, the link girder will also adapt easily. So this makes it really powerful. As you can see, we don't have to change each and every element, but rather we just change it, the main axis, the axis that was referenced when placing the link girders. Of course, we could also change it to any type of shape, so it would also adapt easily. So this makes them really powerful. Of course, I could also change the main axis, which is the main axis that I have here. Before, because I showed you that we have a main axis and we have 2 axes, accompanying axis. So if I just change the main axis, for example, if I change the radius from 1000 to 100, as you can see, everything would also change. So this is what makes it really powerful. Of course, you can also make different other changes as well. Since it's Allplan Bridge, it's also easier to make changes on the fly. The second use case or the second example that I wanted to show you is this cable stayed bridge. So the idea behind this is that you have main girders here, and we have also the main column here. And in these two cross sections, we can place a reference point. After we place this reference point, we have also a link girder. This is also a simple cable element. Using this simple cable element, we were able to place different cables. As you can see, they have different heights, and they are placed in different positions. This was also easily done because we are using the link girders. The third use case, or the second group, because I call this a second group, because in this use case, what I want to show you is the template or the templatized idea of link girders. Like I said before, link girders are based on templates. So we have one template link girder, this one, and based on this, we were able to place all these link girders. So it doesn't make sense to change each and every element when we need to change. So it becomes easier to just change it, the link girder or the template link girder here. So to show you, for example, I will change the width to 8 meters here also, and I will just recalculate. As you can see, all the elements which are based on these link girders, they have also been changed accordingly. So this makes them also really powerful. Another use case, which is also grouped in the same category, is also this truss bridge. As you can see here, we have a truss bridge, which is also placed, because here we have a main girder, where we have these reference points, and from these reference points in the link girder, which is here, you are able to place the trusses. So in this case also it makes sense to have one template or one main object or template and change only that if we require to make some adjustments to our bridge. So it becomes also easier. The first use case or the first group of use case that I wanted to show you is the cross sections. So here, as you can see, the end cross section, we have template here, which is the link girder, and we place this template between this point and this point. So we place all of these 4 piers like that. But one thing that you can notice here is that the end connection or the end cross section is like this. But we can also change that, so it will be horizontal. It will be projected horizontally. We can just make simple change here in the cross section plane. As you can see, we have the option to change it vertical, so it will align vertically the cross section. This cross section area will be vertical. We have also the possibility horizontal, and the normal is the one that's already here. So this was the normal. So I will show you what I mean by horizontal. Here we changed the cross section to horizontal. So as you can see, the end has been also projected properly. So this is also another really cool or really important. The demo that I want to show here is that how the link girders are also parametric. So in a sense that before I said the link girders are based on templates. So if you change this template, all the elements will also adapt accordingly. But one thing to remember is that it's Allplan Bridge, so all the elements are also parametric. So what I want to show you here is that I have added some variations for the elements or for the offsets as well. So these variations, I will just change them here. So what I mean by that is that I'm adding a variation which varies according to the global station from the start to the end. So if I add a variation here, as you can see, these objects or these girders, they have also been adapted or changed as well. We said that before they are based on the templates, so if we add a variation to the template which varies according to the global station from the beginning to the end, it can vary each and every element which are based on this template. So this is also really important feature. To the second part of my presentation, which is IFC 4.3. So by now, many of us are familiar with the IFC, which is a neutral data format. it's based on open beam principles. This is based on open beam principles, which is also a great choice for collaboration. But there is a new release, which is the FC 4.3. This new release, it extended the previous one. It has two really important features of this new release that I want to discuss with you today. The first one is this new release has extended its definition, the definition of the schemas, to include the definition of infrastructure projects, such as bridges, rails, and roads are included in this new schema. And the second really important feature is also the enhancement of the schema or the spatial structure. So this is also really important when we are working with bridges. Bridges, as you know, are really complicated. So to divide a huge bridge into different parts or to collaborate with different stakeholders, it becomes really difficult. So to do so, the spatial structure or the definition has been enhanced, so we can easily break down the bridge. Of course, this was easily implemented in Allplan, since Allplan is a partner of Building Smart and a huge collaborator of OpenBeam. So to show you how this is set in Allplan, I will just go through the options or the possibility to set the FC. So first we have a bridge project, then we set the bridge type in the options. I will also show you later. Then we divide the bridge project based on the bridge parts. That could be pier, abutment, and so on. Then we divide each object or each element in the product. Then later we could also assign them the name. So first, for example, as you can see, we have in the cross section, we have piles. Then first we assign the object type, which is IFC pile for this case. Then later we assign them a name maybe pile number 1, pile number 2, or something. Then after we assign these piles, we assign the group of the piles, which could be the pier or any foundation for that matter. We assign the bridge part type. Then after we assign each and every element, we can see that at the end, we have a division of, or the bridge has been divided accordingly. So this makes it much more easier when collaborating with other stakeholders. Of course, there is also the possibility in Allplan engineering to further add additional attributes. What I mean by that is, for example, we have a bridge, as you can see, and we want to add additional attributes. This might be the information requirement, or maybe it could also be a user's additional wish. So the user can just come here and add additional attributes. As you can see, we have different groups that we can choose from, but we could also just define our new attribute. We have the possibility to set the name, the data type, and the different values. We define two new variables, two new attributes. We define this pile number and unit cost as a new variable. Then we will transfer these new attributes that we define them to the other objects. We can just also do this by using the transfer attributes. Here, as you can see, I will choose the attributes that I want to transfer to the other objects. There is also a really cool feature which allows you to save these new attributes that you define, and also maybe load these new attributes that you define from other projects as well. So it makes it much more easier to transfer attributes between different projects. Here I will show you, or I will demonstrate all the workflows that are required when setting IFC attributes. First, we will start in Allplan Bridge, where we have a bridge here. Here we can set the IFC product type. For example, this is a pile, so we will set the IFC type for this. This is defined in the cross section, so we'll define the IFC type here for the object. So this is pile type of board, so we'll set that. It's also possible to set the name type, so we'll have different names for the same objects, for the same piles. Then after we define this product definition, the cross section, we move to the structural members. Here in the structural members, it's possible to set the bridge part type. So this is the new feature that's released in the 4.3. So here we can add the definition for the structural members. Since this is a pier segment, for the pier foundation, we assign it a pier segment. Of course, we can also do similar thing to the girders, link girders, and decks as well as, and all these structural members. So here we will assign the deck segment. After we assign this bridge parts type, the final thing is to assign the bridge type for the whole project. So here, if we go to the project setting in Allplan Bridge, we have different possibilities to set the different project properties, but at the end we have the possibility to set the IFC bridge type. Here, since it's a girder, we can set it a girder. But you also have other options to choose, but you could also add your own definition. You can just write it in. Then finally, you transfer the project to Allplan Engineering, where if you have a wish to add additional attributes, you can add them here. So here we can make sure that the attributes that we defined in Allplan Engineering, in Allplan Bridge are transferred. You can also observe that the material which was defined is also transferred accordingly. Here you can also observe if you have the tendons, they will also be transferred accordingly. So here we are adding additional attributes. We can choose from the defined groups. We have different groups that are defined already, such as the FC. Or you could also add your own definition or your own group as well. Here's I'm adding an attribute called unit cost with a data type of floating point number. I'm proposing a value of 0, and I'm adding a minimum and maximum values. And we have also the possibility to set the unit of these new attributes that we defined. Here I'm setting it to euro. So these new attributes that we defined is only set for this element, for the pile element, that because we only selected that. So we can easily transfer the attributes that we select from the attributes that we define in this pile to the other elements. So how we can do that is by just clicking on the transfer attributes, then setting the attributes that we want to transfer. Here, as you can see, we only need the unit cost, then we will transfer this unit cost to the other elements. Since we want it to all the objects, we can just easily transfer it there. We can confirm if the transfer was successful by just clicking on the object and going to the properties, and we can find the newly transferred attributes there. One thing I want to mention here is that it's possible to transfer attributes from one project to another project. We have the possibility, as you can see here at the end. Here at the end, as you can see here, we have the possibility to load a favorite or even save a favorite. So it means we can save one attributes from one project to another project and load them there. Finally, we can export the IFC. We can export the project as an IFC. Here, as you can see, we have different options or settings that we can choose from. So here I will choose the IFC 4.3, the standard export. Then I will export that. But one thing I want also to mention here is it's also possible to set the model view definition, but in our case, since we don't need it, we will not set that model case definition. Another really important feature here is also the attribute mapping. So here we can add or we can map attributes that we defined from Allplan to the IFC attributes. Here, as you can see, the attributes that we defined, we can set it to Allplan, to IFC attributes, and we can map it properly. So we just export it as IFC 4.3, then that will be in it. The only thing that I want to show at the end is to show you how we can view this 4.3 in the viewer, IFC viewer. Here, as you can see, we have the bridge, IFC bridge, and we can see that the bridge type that we defined in Allplan Bridge is also transferred properly. So before we said it is a girder bridge, so this is also transferred. And we select, for example, for the structural members, as you can see, the structural member type is also defined here as a superstructure. This also works for the other elements. For the pier, as you can see, it's pier segment. And of course, this is the facility prototype. And of course, for the foundation as well, this is also assigned. Because we assigned it as pier segment, this is also transferred. Of course, if you also click on the piles, you can see they are defined as FC pile, and they will be defined as board. This also works for the pad footing or for the foundation as well. So this was all from my side. I would like to thank you for listening to me. And if you have any questions, of course, you can also send them to the chat box. And thank you. And I would like to introduce the next presenter, which is Jan. It will be really interesting. Thank you.
Hi, and welcome back. First of all, thank you to my colleague Mobile for his very interesting presentation about link girders and the IFC 4.3 implementation. At this point, I would like to formally introduce myself. My name is Jan Ostersch, and I'm a technical consultant at the Allplan Infrastructure Competence Center in Graz. Today, in the next 10 to 15 minutes, I would like to talk to you about two very interesting topics. And these are skewed bridges and the accompanying axis. And I can guarantee you at this point that this will make your daily work with Allplan Bridge even more efficient. But before we start, let's take a look at the content. First of all, we're going to take a look at the skewed bridges. What was our motivation? How do we model them in Allplan Bridge? And how do we apply changes? Here, I would also like to give you a few tips and tricks that will make your modeling experience with Allplan Bridge even better in the future. The second one is the accompanying axis. And the accompanying axis will be first shown the modeling, how it's done. And in the second part, I would like to show you a few use cases that should give you an idea how to use this new feature. So let's get started. First of all, the skew. This is a 3D Boolean operation, and we use the Parasolid engine for skewed section meshing. So we get a very detailed geometry there. So what was our motivation here? We know the bridges usually don't cross with roads in a perpendicular way, but rather at a certain angle. And this results that we have the end or the beginning or both sides from a bridge skewed. And as engineers, when we design our cross sections, either it's on paper, in a 3D model, we usually think of positioning them perpendicular to the main axis. But once we start introducing some kind of variations, the alignment changes, these skew geometries can get very complicated. That's why we have developed the new skew functionality in Allplan Bridge. First of all, I would like just to explain the steps. Then we're going to take a look at a few videos how it's done. First of all, the user defines the master girder or the master deck. I already talked about this topic in my live demonstration before, but to explain it briefly again, when I define a master girder, it happens in a separate 3D environment. This separate 3D modeling environment has all the features that we know from Allplan Bridge, but it can be reused over and over and imported to the 3D model when we decide to do it. The next step, what the user has to do is to position the master girder or the deck. And the last but not least step, which is probably the most important, is the positioning of the skew and the definition of the angle from the user. So the best would be that we take a look at this video now and see how it's done. First of all, the user creates the master girder, as we see in the video now, and this will open up this separated modeling environment. We use the tools we already know, select the section, the axis, select the cross section, position the first station point, the last station point, and define the subdivision. Once the model is created, we can easily apply variations to it. So here, in this case, for the width on the left side, and the same for the right side. When we recalculate this, we will see in this separate modeling environment, we will see the variating geometry. Okay, once this is prepared, we can also decide which stations we would like to transfer to our 3D model and which ones not. So in this case, I will just turn off 2. Once this is prepared, recalculated, I can go back to my 3D model where I have 2 very simplified abutments already created, and I can just use this drag and drop functionality to position the master girder. I will change the name here, The name would be now, for example, Skewed girder, and I will position it on the axis. And now we come to these steps we've already seen before. I need to define the position of the first cut. So this will be at around 30 meters with an angle of 20 degrees, minus 20 degrees. And then I need to position the second position of the cut station at around 65 meters and also with an angle of minus 20 degrees. Once all this is set and done, we just need to do the recalculation, and we will see how now, for example, this master girder applies to the existing abutments. Okay, looks very nice. In the next step, I would like to take a look at how to do changes. We can make changes to suit structures really fast and easy. And in this case, I would like to propose an idea. Maybe use a global variable that can be defined and allows easier control of the skew angle if a change occurs. And also, this kind of handling changes can be applied to any part of the model. So let's take a look. We already have the steps that we have created before, and I will create now a formula which will serve as a global variable. In the field for the expression, I will type the angle, which is minus 20, and I will assign now this global variable of skew angle to the positions where I have already the sections created. This is now done in this step. So this is now at station 31.3 and 65.3. Once this is recalculated, nothing has happened yet because we need to do some changes. We can see we have two transversal axes here in this model, and I will both change the angle from minus 20 to minus 5. But keep in mind, I didn't change yet the angle of the skew. So it will look a bit funny, but we will fix this now in the next step. So now we can just use this global variable and just change one value, and we will see that this master girder will now, let's say, take the shape of the transversal axis. Okay. There is one more thing that you might notice or might have not noticed is that, for example, the model in Allplan Bridge looks a bit polygonized. But don't be afraid, because once we export this model to Allplan Engineering, we get a detailed curve geometry. So let's take a look at this example. On the left side here of the presentation, you see the bridge that was created in Allplan Bridge. On the right side is the model with the detailed curve geometry in Allplan Engineering. Maybe a bit more obvious from the top, we see this polygonized shape at the bottom and at the top, but the same model in Allplan Engineering looks very nice and very detailed. And don't be afraid, you're going to use the model in Allplan Engineering for all your plan production and all rebar modeling. Okay, so this was the first topic, and now let's continue with the accompanying axis. And for the accompanying axis, we can say this is an extension of our modeling capabilities. This is basically an axis that is parametrically offset to the main axis. And this offset can be user-defined, either vertical or horizontal, or both at the same time. It can have a constant value, or it can be defined through a table. And the most important part, it can be used as a normal axis. So I can click on it, I can extrude any kind of cross-section that I have on it as I do on the normal axis. And this could be used, for example, for parallel bridges, side curbs, or retaining walls. So let's take a look at a few use cases. In the first use case, the main axis and the structure are defined. We see in this example, we have a short bridge around 50 meters, a very simplified abutment with one pier. The first step will be that the accompanying axis is defined and positioned with a constant horizontal offset to the main axis. So let's take a look at this video. How do we create the accompanying axis? We right-click on the main axis, click accompanying axis, select station range, in this case from the beginning till the end. And I can already here define the horizontal offset, which will be, in this case, 10 meters. We see that the accompanying axis appears here in a yellow color. If we take a look at the axis plan, we see how these values are calculated and that basically every point is offset 10 meters. I've also said this is parametrical, and that's why I'm changing the main axis here and changing the radius to the other direction. Once I recalculate this, I will also see that the accompanying axis accompanies the main axis. So we still have the same offsets, but turned in another direction. In the next step, we will apply some variations to the accompanying axis, and then we will create the geometry of the retaining wall. So let's take a look. We have here now in this video what we've created in the previous steps. Axis plan, still offset of 10 meters. We didn't change anything, but we have a variation table prepared already with 4 stations, and we have different kind of transitions from linear to spline. I apply this by typing in the table name into the correct position. So here at the offset table bracket, so this will be width right. Once I recalculate, I already see how the geometry of the accompanying axis changes. If we take a look at the axis plan now, we will see that it doesn't have constant offset anymore, but rather follows the definition of the position from the table. Now I can use, for example, the functionality to create a new girder, and this will be, in my case, the retaining wall. I will select, as I would usually do, but in this case, the accompanying axis. I will assign the correct cross-section, and I will define the first station, which will be at around 49 meters, and then also the last station, which will be at the end of the accompanying axis. I just picked a subdivision of 2, and we can see how nice this retaining wall was created. And if we take a look from the top, we will see that it follows the definition of the accompanying axis. So this was use case 1. Use case 2 will be the vertical offset. And here again, first the main structure is defined. We have a simple main girder here with a length of 50 meters on a straight axis. But now the accompanying axis will be defined with a vertical offset, and we will use first a constant value, and then we will create a table. So let's take a look how this is done. The steps are the same as before. We create the accompanying axis, set the range. In this case, I will set the range, starting station will be at 6 and go till 44 meters. Okay, accompanying axis created. I will now define the vertical offset. I will say -5 meters, and we can already see this accompanying axis appear below the structure. If I take a look at the profile, I see the additional data and see exactly where it is positioned. But now we have a variation table of an arch created, consisting of 3 stations, and I will just apply this name to the table for height, arch, and once I recalculate, I see that the accompanying axis takes the shape of this arch. But of course, also this arch will now follow if I change the alignment like I'm doing now. So the bridge is not straight anymore, but we say with a length of 50 and the radius 250. So we have a curved bridge geometry now. If we take a look from the top, we will see that the arch also follows nice the alignment. Okay, now in this step, we have created just the accompanying axis, but now we introduce some kind of structure to it. You have maybe seen this bridge already before. It's an arch bridge created also with the help of link girders. But what happens if I change this now? If I change the alignment now? I will change the axis plan again from being straight to curved, and we will see how also the arch and the link girder follows the new alignment. So let's take a look. Length again, 50 meters, but the radius will be now 250 meters. Go with OK, recalculate, and we see that also the arch has now followed the new alignment. So this saves a lot of time and a lot of remodeling that we don't need to do because everything is done automatically. Last but not least, of course, as I said, is the horizontal and the vertical offset at the same time. We will see in a short video how this is done. So let's just take a look. We have one axis defined. We define one accompanying axis. I will set here the full station range from beginning till end. And I have 2 variations tables already prepared, one horizontal and one vertical. I will assign both of them to the axis at the same time. So at offset table, I will type in horizontal, and the table for height, I will say vertical. After less than a second of recalculation, we already see the change geometry of the accompanying axis. But to prove it, let's take a look at the axis plan and the axis profile, and we see that the accompanying axis follows the defined position from the table. At this point, I would like to conclude my presentation. I would like to thank you for joining me, and I hope you have seen something very interesting today. I would like to give my word back to Željka. Thank you.
Thank you all. That was really fantastic insight into only some of the functionalities available in 2022 version. You saw Allplan Road, the new specialized modeling approach for precast girder bridges, advanced pier definition, new types of stations, solving the problematic of skewed bridges, then a new IFC 4.3, accompanying axis, and also completed reinforcement design and code tracking according to AASHTO. Related to this, I would like to mention a few more small but very powerful functionalities of Allplan Bridge that can speed up your daily workflows significantly. One of them is undo and redo, a feature that is not necessary for parametric modeling, but it is now available for you and for maximum user convenience. Another very useful function is also the new measurement tool in 3D, which is allowing the measuring of distances between the two reference points. There are many more functions, improvements, extensions. For example, the extension of the design and checks according to Eurocode with the Brittle failure check. But I would like to point out another one related to a great Python part technology, which is directly connected to Allplan Bridge model, which gives you even more parametric behavior to your bridge model. You can access the Python parts directly from Allplan Bridge and place them parametrically, as you know. Furthermore, not only the object itself can be accessed, but also its parameters. This allows you to either set the parameters manually or the values of parameters are taken directly from the 3D model. From this version, it is not only possible to access the Python part library in Allplan Bridge, but also to visualize Python parts, which tremendously improves the handling of the model. I want to thank everybody for this great content once again. And a big thank you to all the teams that were involved in the development, which are shaping our product with their passion and dedication. And a special thank you to all of you watching us now. Allplan Bridge and Allplan Road are a product of our collaboration and are based on our opinions and on your opinions and wishes, suggestions and feedbacks from customers around the world. In that manner, we would like to invite you to contact us and closely work with us in order to bring your wishes into one of the future versions. It is very important to us that you are satisfied and that you are successful in your projects. Speaking about that, I would like for the very end to show you several ongoing construction sites from the great projects of our power user Yüksel Proje from Turkey. As we can see here, Zigana Bridge, Rize Artvin Airport Bridge, and Oran Viaduct. All the projects have been modeled and detailed using Allplan, and the complete project documentation was also prepared for the construction site. And with this, we are concluding today's webinar. You can also download the test trial version, as you know, and try all these great functionalities by yourself. Thank you for taking your time today, and I hope that we will meet soon live. I would like to invite my colleagues to join me here, and until then, take care and goodbye from us all from Graz. Bye. Bye.